ago. Yeah, like you said, this.
We'll have a chance. So yeah, we are actually we are perfectly on time, so I can start with the presentation. So our next speaker will be N.A.Obers from Nordita and Niels Bohr Institute. And I can say without any doubt that this is the speaker whom I've known the most among the speakers of today, with maybe one exception. Because actually I knew Niels since he was a graduate student in Berkeley in '87. Right?
That's right.
It's a great pleasure to see Niels again. He will talk about torsional string Newton-Cartan geometry for non-relativistic string.
Thanks a lot, Massimo, for this nice introduction, and it's great to see you also again, and the rest of the audience. So at this late hour in Scandinavia, it's half an hour past midnight. I'm going to be talking about some work I did recently with Leo Bidusi, who was a PhD student in Edinburgh, and Troels Harmark, faculty in Copenhagen, Jelle Hartong, faculty in Edinburgh, and Gerben, who is a postdoc in Copenhagen. So the main part of my talk will be centered around this latest paper, which sort of builds on a series of papers that have appeared over the last sort of 5 years in combination with different people. Let me see how the scrolling goes. Yeah. So this talk is about non-relativistic string theory, and in particular, a novel type of target space geometry that we recently found to describe this. But in fact, there has been in the last many years, 5 years, a lot of activity already centered around non-relativistic string theory. In fact, also relatedly, non-relativistic quantum field theory, non-relativistic gravity. But focusing more on string theory, here are some motivations why non-relativistic string theory, or the corner of string theory as we know it, that has non-relativistic features such as a non-relativistic spectrum, why that might be interesting. So first of all, this could be perhaps simpler UV complete theory of gravity. It will not be the UV theory, complete theory of general relativity, but as I will sort of illustrate in the next transparency, possibly a UV complete theory of a non-relativistic corner of Einstein gravity. And perhaps we, since string theory is quite complicated, perhaps by going to this simpler case, we can learn some lessons that we can transport to the relativistic case. Another related motivation to study non-relativistic string theory is, so just as relativistic string theory in a beautiful way through the beta function, so the quantum consistency conditions of conformal invariance, gives rise to Einstein gravity coupled to other stringy fields. Likewise, this studying non-relativistic string theory can give us insight into non-relativistic gravity theories via their beta functions. And in fact, quite some works have been done in that direction already. Another motivation is that ADS-CFT is a very beautiful dictionary between gravity theories and conformal field theories, but still very hard to fully penetrate, especially in the regime where n is finite. So in the regime where you take into account gravitational coupling. So that also motivates that to look at limits of ADS-CFT, and in particular non-relativistic limits. At the end of the talk, I will briefly say something. It's not really the topic of this talk. But in these non-relativistic limits of ADS-CFT, also non-relativistic bulk gravity theories and corresponding non-relativistic string theories play a role. Another sort of interesting reason that which was found about 2 years ago, I think, is that doubled field theory, which is a nice approach to that I guess most of the people here have heard about, doubled field theory and exceptional field theory. It's a nice approach to study non-geometric backgrounds in string theory. It actually is closely related to non-relativistic strings and was shown to be contained in this larger framework. Yeah, finally, well, that it's a rich limit of string theory, I hope will become also clear through this talk, but the study of the non-relativistic sectors of string theory also points at interesting novel classes of sigma models of types that have not been studied before. And just to put a little bit more in perspective, this relation to learning lessons for relativistic string theory. I've drawn here the rather famous Bronstein cube of physical theories. If you sort of look at the theoretical frameworks parameterized by having quantum effects governed by h bar, gravitational effects governed by Gn, or effects that take into account that the speed of light is finite, then we get this Bronstein cube of physics. And okay, I will not go through all the corners, but the holy grail, of course, is to understand the corner where all these three constants of nature are taken into account, which is quantum gravity, string theory being a promising candidate for that. But if you think about it, most of our thinking about quantum gravity or string theory approaches it either from the quantum field theory side. We ask ourselves the question, how can we include gravity effects starting from quantum field theory without gravity? Or we approach this from the general relativity side, general relativity being a classical theory, and you ask yourself, how can I quantize it? But if you look at this cube, there's also sort of a seventh corner here through which you can approach this eighth corner, namely non-relativistic quantum gravity, which would be the UV completion of a classical theory of non-relativistic gravity. And here I should note, and again, that's not the topic of this talk. I could give another talk on that based on some work of a year ago. But let me just note here that non-relativistic gravity is more than just Newtonian gravity. It encapsulates it, but it includes more, and it actually has a formulation in terms of geometry. That will be important for this talk, maybe a variant, well, not a variant, it's an alternative to pseudo-Riemannian geometry, namely Newton-Cartan geometry, that enables you to write such gravity theories in a geometric way. So you should think of non-relativistic string theory as sitting at this corner. It's interesting in its own right, I believe, but you can also hope that just as we like to approach this corner from here to here, we can learn lessons and turn on the finiteness of the speed of light, do some perturbative corrections in 1 over the speed of light to approach the relativistic case. And last but not least, just as holography is a duality between these corners, as I alluded to in the previous transparency, we're also seeing signs that likewise there are holographic correspondences involving non-relativistic quantum field theories or quantum mechanics and non-relativistic string theory. So this is sort of an overview slide. I will not go into too many details, but just to say that non-relativistic strings on flat space-time, in fact, already go back 20 years to the work of Gomis and Oguri and also Danielson and collaborators, where at the time people were very interested also in certain limits of string theory, matrix theory, non-commutative open string theory, all kinds of theory was also a limit of M theory, but and in this sort of larger framework, Gomis and Oguri considered a certain limit of relativistic string theory that they called non-relativistic strings, for the reason that the spectrum had non-relativistic features. Then actually, so what happened? As I emphasized, they considered the string theory on a flat space-time, and with a sort of a renewed interest in non-relativistic geometries, Newton-Cartan geometry being the sort of simplest example of that, and I will review that in a second. But with the advent of interest in non-relativistic geometries, people started to look at various groups at how does this string theory look like on a more arbitrary curved space background. And you find various types of Newton-Cartan geometries were proposed. In one approach that used null reduction, a formulation was found in terms of non-relativistic strings on so-called torsional Newton-Cartan backgrounds. And in another closely related formulation, non-relativistic strings on a target space called string Newton-Cartan, SNC, were found by these groups of authors. I should say there's also related non-relativistic strings in these works. Tensionless strings are sort of an avatar of non-relativistic strings, Galilean strings examined here, and I also already mentioned the relation to double field theory. Are there any questions about the motivation or this quick background? Just interrupt me. Now, so where this talk sort of starts is that there are some issues with these formulations that were found in the last years. And one is that the string action formulated on the strings in Newton-Cartan geometry exhibits a Stuckelberg symmetry. A priori, there's of course nothing wrong with that. With the Stuckelberg symmetry, it means there's some kind of field redefinition that leaves the action invariant. But it suggests that there is an over-parameterization of fields and perhaps alludes to that there could be a simpler formulation in terms of a set of smaller set of fields. Another maybe very technical sounding aspect, but I still mention it, and I will also come back to it, is that in this formulation, there's a certain underlying symmetry, the so-called ZA symmetry. You can think of it as the analog of the mass symmetry for a non-relativistic particle, so the generator of mass. And this symmetry, imposing this symmetry on the string action, put some constraints on certain properties of the target space-time, namely its torsion. And it has puzzled us that when we do null reduction, we get a very similar action, but we do not get such constraints. And then there's also, I'll skip over this point, there's also an extra symmetry generator in the underlying algebra for which there's not a corresponding field. That's maybe a priori not the problem, but still something that makes you wonder. And so that motivated us to revisit the formulation of non-relativistic string theory and its target space geometry. Just to give the main result or main punchline, maybe it doesn't mean yet so much when I say it here, but you might then remember it at the end, is that we find a formulation in which the target space geometry contains a two-form field. And you might right away think, okay, ordinary strings also have a two-form field, the B field, right? And it's in fact, sorry, closely related to it. But it has a very special property that this two-form field, it couples to the tension current of the string. And that's very natural, as I will illustrate by discussing the non-relativistic point particle in a second. And it transforms non-trivially under string Galilei boosts. So it is actually an intrinsic part of the geometry. Just as, and again, I'll review this, for the non-relativistic particle, there's a certain coupling to a one-form gauge field that is of a similar nature. The other result is that you find this geometry via two different routes, and that's a nice consistency check, either via a null reduction of a relativistic string in one dimension higher, or a C going to infinity limit of the string action in a given dimension. And again, I will review how this, just as a warm-up, how this works for the particle. And the final result then is that to a geometry you can associate a symmetry group in algebra, just like to pseudo-Riemannian geometry you can associate Poincare symmetry, as we all know. So the geometry that is associated to this new target space geometry for non-relativistic strings that we find is a novel algebra, and you can actually get it, and that's also the way we will get it here in this talk, as a Inoni-Wigner contraction, not of the Poincare algebra by itself, but of a stringy version of the Poincare algebra, namely the Poincare algebra plus the algebra that extends this with the symmetries of the Kelp-Ramond B field. So in that sense, you need the full NS sector of string theory, and then perform an infinite speed of light limit to get this algebra. So, but yeah, I will detail some of these statements in the time to come. So here's an outline of my talk. I'll first give an introduction to Newton-Cartan geometry for particles, not for strings. Not only to be pedagogical, but it will certainly, hopefully, later in the talk show you that what's going on for the string is entirely analogous, but now it's not. It's a stringy version of it. And in particular, I will show you how you can get the coupling of a non-relativistic particle to Newton-Cartan geometry through either the C going to infinity limit or null reduction. Okay, then I discussed the main result of this talk. And at the end, I will also zoom out a little bit and give you a little bit more of a bigger picture. And in particular, one of the things I want to emphasize is that we see this for particles, but now also for strings. There is a difference between considering really strict speed of light to infinity limits, as opposed to taking a theory and doing a 1/c expansions. It maybe sounds trivial, but in terms of the types of couplings and the types of geometries you get, there are some important differences that I will try to sort of give an overview of. And yeah, then I will end with some outlook. Any questions at this point? Okay, I don't expect the audience, except for maybe very few, to know what Newton-Cartan geometry is. So, and I will, derive this also for the point particle case. But let me first, just very broadly, give you sort of a lead of what this is. As I told you before, the geometry of space and time is intimately related to the local symmetries of space and time. We know this very well for GR. Pseudo-Riemannian geometry is related to local Lorentz symmetry that embodies the Einstein equivalence principle. Now, in the same way, and actually that's post-Einstein, Cartan, he asked himself the question, well, we have also Newtonian gravity. Newtonian gravity by itself is also a diffeomorphism invariant theory. Actually, any theory should be invariant under coordinate transformations. So the fact that Einstein managed to geometrize gravity should not be just exclusive to general relativity. One should also be able to find a geometric underlying dynamical geometric principle for Newtonian gravity. It's just that the geometry should be different. And so that led him to find Newton-Cartan geometry, which in the same way as in this case makes not now Lorentz symmetry local, but Galilean symmetry local. And it enables you to write down Newtonian gravity in arbitrary frames. Now here, so here, let's do our workup, our warm-up. Let's first look at how you can get Newton-Cartan geometry. In fact, it has torsion. I will spend a transparency on that. How do you get this geometry from null reduction? Consider a Lorentzian metric in, say, one dimension higher than you want to be, with a null isometry. Then you can show that the most general metric with a null killing vector that you can write down takes this form. So here the null direction is u. My d+1 indices are m, mu run over d in indices. So this is the extra direction, the null direction. And this geometry in this general parameterization, it features a time-like field line, a spatial metric, which is degenerate, there's this signature, but it's still a tensor, and a U1 vector field, mu. These fields here, tau, h, actually define for you what is Newton-Cartan geometry. You can show by from the transformation properties of the metric, by looking at this form, that the way the local symmetries that act on tau, h, and m. Yes.
A question. Is there a misprint in this equation, because I see only one differential in the first instead of an expression that's quadratic in differential?
Oh, yeah, thanks. See if I can correct it. It should be a tau mu dx mu. Here. Okay. Thanks a lot. It's because actually, yeah, right. We often write tau, but then we mean the tau is tau. Tau is a one form, but I shouldn't have written them here. Thanks. So you can show that these geometric variables. So this is what replaces the metric g mu nu in a Newton-Cartan geometry. Time-like field line, spatial metric, extra U1 gauge field. They transform like so under, well, they are tensors under diffeomorphisms, but where I transform non-trivially is under Galilean boosts. So this is inert on the Galilean boost. This transforms in a certain way on the Galilean boost, and the same with m. And in addition, there's the U1 isometry, of course, corresponding to shifts in U, and it acts like an ordinary U1 gauge transformation on M. This is very algebraic, so very sort of very technical, but I'll get to the interpretation of this. But let me just also give a drawing. So one way to think about Newton-Cartan geometry is you have time, spatial slices, and on every point in space there's a U1 gauge field. This U1 gauge field is very natural to understand, because in a non-relativistic theory, energy and mass are not the same anymore. So the response of the field theory, for example, coupling to tau is energy. So here the response to this is energy, and the response to this is mass, current, energy current and mass current. So it's just from thinking about field theories, non-relativistic field theories, and the fact that energy is not equal to mass, sort of makes clear that the geometry should also have this extra U1 mass gauge field of mass. What's quite important is the kind of properties that this time-like field line satisfies. If tau is exact, then you have absolute time. This is actually the geometry that Cartan introduced. Not surprisingly, because Cartan wanted to have a geometry for Newtonian gravity, and Newtonian gravity has absolute time. But what has only been realized, say, more recently, well, in the last 7 years, so it's not so recent anymore, is that the generalization, so allowing more arbitrary versions of tau is quite important. And in that case, you can actually show that the geometry has intrinsic torsion. So it's not an extra degree of freedom, but you can show that the torsion defined as the antisymmetric part in the connection is non-zero. So if you have no conditions on tau, we call this the geometry TNC. And what's rather important is sort of an in-between case where tau is hypersurface orthogonal, called that twistless torsion. And yeah, in that case, you have a preferred foliation in terms of equal time slices. So here there's a notion of causality, and if you're here and this is not true, then your space-time would not be causal anymore. Now, how do you actually get the coupling of a non-relativistic point particle to this geometry? There are actually two ways. You can do a null reduction of a relativistic point particle, or you can do a C going to infinity limit. I do it a little bit quick because you can also see the time is going fast. But just to give you the basic idea, we all know the action of a non-relativistic particle. We insert the form of the metric that has a null killing isometry. We write it out. There's a natural structure appearing here, H bar that's built out of H and tau and M. And then you'll find that because we have an isometry in the U direction, the momentum in the U direction is conserved. So it should be a constant, and it will actually get the interpretation of the mass of the non-relativistic particle. So you can use this to eliminate E, and out comes this action. So this is the action of a non-relativistic point particle of mass m, coupling to a Newton-Cartan geometry. What's maybe not so clear here, but if you insert this here, right, you see some coupling of mu dx, yeah, roughly mu dx mu sitting in here. And so in fact, the response to varying this action with respect to mu precisely returns the mass current. That's what I said just roughly before, right? So, and also if you have a field theory coupled to Newton-Cartan geometry, the response to mu will be the mass current of this field theory. Like, for example, Schrödinger theory. What's important, and actually this was very nicely shown in a paper, I think by now 2013 or 12 by Eric Bergsoef and the rest of the Groningen group, is that you can actually get this geometry, TNC geometry here, and its transformation properties by gauging the Barkman algebra, which is the centrally extended Galilean algebra. So it has boost translations, Hamiltonian, and here this mass generator, which is the generator dual to the gauge field mu. And this gauge field mu, essentially its time component has the interpretation as Newton's potential phi. Now you can also get this action by not null reducing, but by staying in the same dimension and doing a limit. What's very crucial is that you should take now a limit of a extremal relativistic particle, extremely charged. So the way that works is like this. Here we have the action of a charged particle. So far, the arbitrary charge q. You now plug in. You want to get ready to do a C going to infinity limit. So you have to remember that there's a C squared in the, in the 0, 0 component of the metric, and you can write it in a covariant way like this. And then you can expand this for large C, this action, plug it all in. And what you see here is that there's a diverging term going like mc squared, but precisely for an extremal particle with q equals mc squared, you can cancel this divergent term by redefining your relativistic time like field by field and your gauge potential in this way. And yeah, I didn't write it up further, but if you then do the limit, you will actually find this action again. At the algebraic level, what this procedure here and also this field redefinition, what this entails is that you redefine your original momentum and the original charge operator here Q into a new Hamiltonian and a mass generator N, and then you take the C going to infinity limit. Now at the algebraic level, that means you're doing Inoue-Wigner contraction. So essentially you're getting here the Barkman algebra from a contraction of the Poincare algebra times a U1, where the U1 comes from the charge. Now, this sounds all maybe very trivial because I think many people have shown you, but in string theory, if you take into account the B field, you can find a very analogous setup, and that will give rise to the novel geometry that we found. So, and what will also be crucial in this is that the string, the fundamental string itself is an extremal object. The fundamental string has the property that its mass is equal to its charge, or rather say its tension is equal to the charge, as we know from the Nambu-Goto action. So what's our starting point? Well, let's first revisit the B field that we know in relativistic string theory. I actually want to now first find an sort of underlying algebraic way to understand the B field in string theory. So the metric in the B field in string theory transform like this. There are tensors, of course, and then the B field transforms also under gauge transformations. You can ask yourself the question, can you get these transformations from the gauging of a certain algebra? Just like this can be gotten by a certain gauging procedure of the Poincare algebra. It's not direct gauging, but it's a gauging procedure where you transform, say, the local translations that the Poincare algebra has. You transform those into diffeomorphisms. Now we want to do something more. We don't only want to have diffeomorphisms, but we also want to have the gauge transformations of the B field. Well, what's the algebra that you might guess that does this job? It's the following string extension of Poincare. So we have the Lorentz generators, the translation operators, and we're going to introduce a second set of translational operators, Q. This is, and it's more than just inspired. Well, we were inspired by double field theory, but I'm sure there's a much closer connection to double field theory, in fact. But so let's take this, let's take this and run with it. So we have a second set of translational operators. Now we're going to introduce a Lie algebra valued connection in this group. You know, the gauge generator corresponding to the translations is, as we all well know, as the field bind. This would be the spin connection. Will not enter the metric. But what I want to focus here on is the extra gauge connection that you now get that corresponds to this extra translational operator. The statement, and I'm not going to show you the details, but I'm just going to state it, is that if you construct the metric as usual, just as this invariant rotational invariant combination of the regular field binds, and construct the B field as this anti-symmetrized combination between E and this new gauge connection pi that corresponds to these extra translation operators, then you can show that the group transformations in this string Poincare algebra generate these transformations. The counting works, right? Like you have D, you know, just as you have this dimension D worth of translations, giving diffeomorphisms, You have now also dimension d worth of extra gauge parameters corresponding to these, which will give you these gauge transformations of the B field. It's a little technical to show, but believe me, it works. So the essential thing now I want to use is this fact that B is actually tied to the metric in a certain way, right? Because we have here E and we have here E. And now I want to mimic the C going to infinity limit that I showed you for a point particle. Acting now on the string action. So the string action, as we all well known, is number go to plus the Sumino term, square root of the determinant of the metric, coupling to the B field. We're going to use, as I announced, this form of GMB. And that was also followed by the papers deriving string Newton-Cartan geometry. Now we're going to make a split of the tangent space into two longitudinal directions to the string, call them capital A, and the remaining transverse directions, small a. And we have to reinstate factors of C, and we're going to open up the light cone, but the light cone opens now up on the string world sheet. Like in GR, the light cone would be just opening up only in one direction. Here it opens up in two directions, the longitudinal directions. And you do that for the regular field bind and for, let's say, the B field bind. And okay, we're gonna mimic this redefinition of the time-like field bind here, and the gauge field here. We're gonna mimic that here now in a two-dimensional way, because remember A goes from 0 to 1. And again, if you do that, you find a similar type of cancellation. This has been noticed also before. It's nothing new, because the string is extremal. But what you're left with is the following action. So it contains, you can see this as a kinetic term. It involves the spatial metric contracted with inverse time-like field binds on the string, and a coupling to a field M that takes some very specific form in terms of these gauge fields that we introduced. But so I just want to juxtapose this to what I just showed here. So just as for the particle, the geometry is given by a time-like field bind, a spatial metric, and a one-form gauge potential. For the string, one finds actually a very natural generalization. A time-like field bind, but now with a going in both longitudinal directions along the string, a transverse metric, and now because it's not a particle anymore, but it's a string, a two-form Newton-Cartan gauge potential. And in fact, you can precisely see that this Newton-Cartan gauge potential couples to the world sheet tension current, just as for a particle, mu couples to the mass current. And you can actually see here, in some sense, that the string satisfies some weak equivalence principle, because the prefactor here of the kinetic term, that's like the the inertial mass or the inertial tension, and the prefactor here in terms of the coupling to m, because you can view m as the gravitational potential, as one can show with a little computation. The coupling here, which is also T, can be regarded as the gravitational tension of the string. So non-relativistic strings satisfy the weak equivalence principle. Again, in their equations of motions, the tension would drop out. Now, once you have an action, we also, of course, want to know the symmetries. This action obviously has a gauge symmetry acting on the two form. But what's rather non-trivial is that it has a string Galilean boost symmetry that mixes these two terms, but in such a way that the sum is 0. And so in particular, on the string Galilean boost, the spatial metric transforms non-trivially. This is the parameter of string Galilean boost, and the two form transforms also in a certain way and in such a way that the action is invariant. And this is really the string analog of the symmetries that one knows for the non-relativistic point particle. Now, once you have these symmetries, you of course would like to know what's the underlying symmetry algebra, just as the underlying symmetry algebra for a non-relativistic point particle is the Barkman algebra. It turns out you can get it again from an Inonu-Wigner contraction. And recall, I told you the Barkman algebra can be gotten from a contraction of Poincare cross U1. Here we're going to get it as a contraction of not just Poincare again, but of stringy Poincare. Now remember, stringy Poincare had Lorentz generators, translation operators, and a second set of translation operators, the Qs. So what we should do is we should decompose them again in longitudinal and transverse directions. You just write down a bunch of generators. We should implement, and that's very crucial, because you actually do a basis transformation and then you do the C going to infinity limit. You should implement a basis transformation, which follows from this redefinition of the field lines. And then, long story short, if you do that, and you take the C going to infinity limit of the algebra, which is now a novel algebra, it's the Inonu-Wigner contracted algebra. You see, I didn't write down the full algebra, but the essence is these commutation relations. Okay, and then there are a lot of commutators involving SO11 and SOD-2 rotations. But the crucial feature is that stringy boosts, the commutator with the string Hamiltonian, so the world sheet Hamiltonian, it commutes to P, but also in another way with an epsilon symbol into Q, and stringy boosts act non-trivially on P and Q, but they actually stringy boosts commute with each other, and I'll comment on that in a second. Yeah, so that's this algebra, and then you can again check that from this algebra you can derive these transformation rules. This is more like if somebody asks, one can compare this to the SNC algebra, but and to the action, but I think I should, in view of time, since I only have 8 minutes, I will skip it. But if you want to ask at the end the comparison to the so-called stringy Newton-Cartan action and algebra, I can show you transparency. What's satisfying is that the same geometry can be obtained also by null reduction. And again, in analogy with the point particle, you would expect that this is the case. So I will not show you how this goes, just take my word for it. The way it goes, you start from the Polyakov action, including the P field, and you reduce this along a null isometry. You implement conservation of string momentum along this null isometry, and you do that using Lagrange multipliers. And then there's actually a nice trick that is sort of reminiscent of T-duality, but it's not really T-duality because it involves null direction. But you can go to a dual formulation that exchanges the fixed momentum along the null direction for a fixed winding of the string along a compact dual direction. And when the dust settles, you find the action I showed you here. And you can also find in that way, with a little bit more work, these symmetries in particular, these symmetries here. Just some, because I only have 5 more minutes, I see some words on limits versus 1/c expansions. You can start with some sort of probe, either a probe action or a dynamical action. and find to a C going to infinity limit, and in that way find a limit geometry. And I'll give you a table overview in the next transparency. But okay, for lack of creativity, we call that root type 1. In that way of doing, when you take C going to infinity limits, it's very important that if there is a divergent term, and often there is, that it should be cancelled in some way. And yeah, I hope I've shown you that the way it's cancelled is precisely for particles, because you take an extremal particle, and for strings, because strings by themselves are already extremal in the sense that the coupling to in the Nabu-Goto term is the same as in the Wessel-Minimal term. So that's type 1. You can also get non-relativistic geometries from expansion. So not a strict C going to infinity limit, but just take an action and assume some analytic behavior in C, the speed of light, and an order by order compute terms in the action. And at each order, you will then see more and more gauge fields that ultimately should resum into the full relativistic metric, for example, if you do gravity. Again, for lack of creativity, we call that way of doing type 2. Now, this talk was about type 1, but now, so at the end, I would just want to make some remarks about type 2. Well, what sort of the overview of what you get when you do an expansion and not a limit. Actually, for the particle and also its coupling to non-relativistic gravity, this was done in some earlier papers here. And for the string, in particular, some recent paper here appeared. And sort of what and I will not go through this entire table, but what sort of emerges is that in the type 1 case, be it particle or string, okay, this is geometry here, this is here, this is what I talked about. One does not find any torsion constraints. One does not find any constraints on tau. If you take the type 2 perspective, then you often find, and that's quite interesting, that there are dynamically related constraints on the torsion. And they're typically determined by the equation of motions of the target space fields and the embedding scalars. So, okay, so here you see that at each order of your expansion, you get more and more gauge fields. And yeah, and it's also known at each order what sort of the underlying symmetry is. But that's really sort of the punchline here is also that there's really sort of a distinction between thinking about type 1 and thinking about type 2. I will skip to the outlook. So there has already been quite some work on beta functions for non-relativistic string theory. Some very interesting results, one for the so-called SNC formulation and also for the so-called TNC formulations. And they're all very interesting. They describe the dynamics of some versions of non-relativistic gravity. But so for the outlook, it would be, you find various types of torsion conditions also dynamically in these beta functions. So one point that would be interesting to examine in the future is using this new formulation of the target space geometry. What happens to these torsion conditions? So for example, for the SNC string, there's an important torsion condition, like so found on the time-like field binds. A set of other problems, and there are more, but I just mentioned the main ones, is full stringy geometry in the NS sector does not only have the metric and B field, but also the dilaton. And it could be interesting to also include the dilaton field in this analysis. There's a whole relation to doing a further non-relativistic limit on the world sheet And it's actually those type of sigma models. So when you do, again, a second non-relativistic limit that are, so these are really non-relativistic 1+1 dimensional sigma models that we are quite interested in because they can be related to certain sectors of the ADS-CFT. So we're working on that. Another obvious generalization to look at is apply this same limiting procedure to extremal p-branes and find the analog of the geometry I presented here. Find some connection to D and M branes. There's been some already interesting recent work in just this year. Relations to the open string sector and DBI actions. Also there has been recent work. And yeah, always an obvious generalization, but I think also obviously interesting here is the supersymmetric generalization of the geometry, and even the supersymmetric generalization pre the limit, so of the stringy Poincare, and which then would include Ramon fields probably, and relations to exceptional geometry would be interesting to look at. Okay, thank you. I'll stop here.
Thank you very much. Thank you very much for your talk. And now it's time to ask for questions from the audience. You can just raise your hand or ask viva voce.
Hi, Niels.
Please.
Hi. Ah, you're still awake.
Yes. So I hope I didn't miss it, but what about the quantization of these strings and the like? What is the spectrum? Can one define like a world sheet for calculations like vertex operators or something like this?
Yeah. Yes, for sure. And yeah, this there have been beautiful papers written on that, in part by Eric Bergsoe, who's here, but also Ziki Jan, who's at Nordita. So that's the approach they have been following to compute beta functions for the stringent Newton, for the strings on stringent Newton-Cartan geometry. So yes, there is a whole world sheet formulation. And corresponding beta functions. So what I tried to say here, or I'm not sharing my screen anymore, is that so those beta functions are formulated in terms of a different target space geometry, and it would be interesting to reformulate them in terms of this target space geometry. That's probably a relatively easy exercise. What's more interesting is to see, and that's where it becomes a little bit intricate, is what happens to torsion conditions. Because in these world sheet calculations, it appears that certain torsion conditions come about. But maybe with this formulation, there's something different about these torsion conditions. But so, yeah, I can highly actually, well, small audience here, but Eric Bergsoe and Dieter van der Bleek and Jelle Hartong and Shira Chapman and I were organizing school at Nordita in, I think, 2 weeks. Ziki will give lectures there, and I'm sure he will focus on this world sheet formulation. So if you're interested, I can give you a link that you can hear more about it. He has also developed it quite well for the open string sector. Just to give one concrete answer on the spectrum, because I included it in my talk, but in view of the time, I quickly. So the spectrum. See if I can.
Okay.
So here at the bottom, you see the spectrum. So for one thing, there are no massless states, but maybe that's not surprising. And you also need a certain non-zero amount of winding this W is the winding around a compact longitudinal direction. R effective is the
is there a
it's
tachyon?
the radius. In the there's tachyon in the bosonic case. Not much has been done for the super symmetric case, so I don't dare to say. The expectation is that tachyon would be eliminated in the super symmetric case. But so, for example, a very beautiful calculation, and that's just in flat space. That's beautiful calculation, 20 years old by Comis and Ogori, is that if you look at the 4-point function of 4 tachyons, but there is a certain amount of winding, then you recover a Newton. Well, you can extract from that 4-point function in momentum, for example, in momentum space, Newtonian potential. So you see that that states are interacting according to Newtonian gravity.
Thank you. I have one question. Is there a critical dimension for this non-relativistic string? Is it the same?
Yeah. Yes, it is this. Yeah. So it depends how you count, but it's also 26 for the bosonic case. Actually, so the critical dimension does not change. And okay, that was found through these papers doing the quantization. Okay, and there were 2 formulations, but the one based on one formulation was done by a Utrecht group, Umut Gursay and collaborators, but both find 26.
Thank you. Thank you very much. So let's thank Niels again for his talk, and we good to see you again. And let's have a little break, just 3 minutes, and then at 1/2 we'll reconvene for the last talk of the day by Professor Naoki Sasakura. So in the meantime, the last speaker, maybe you can share the screen.
Thanks a lot.
See if everything works.